Kia ora, Robert McLaughlin here. Welcome to lecture 3 of week 10. Now just remind you to start off what we saw last time, which is that if we have a fixed point x hat y hat of a planar vector field like this, we can see what happens near those fixed points by looking at x minus x hat. That would be a little vector that points from the fixed point to the current point x. And then if we linearize and ignore the higher order terms, we get the linearization du dt equals a times u. The linearization of the nonlinear system at the fixed point x hat y hat. Now we know how to solve that, and we can easily determine the stability of the linearization. And the question is, if u equals 0 is a stable fixed point of the linearization, does that mean that x equals x hat was a stable fixed point of the original nonlinear system? That's quite a significant and difficult question. And this theorem 10.3 in the textbook answers that question. We're not going to prove it, but it certainly, you can see why it would be plausible. If all the eigenvalues have negative real part, then all the solutions of the linearization all look like e to the lambda t, where lambda has negative real part, and they all tend to 0. Now, if the u is tending to 0 very quickly, then the higher order terms like u squared, they'll be even smaller, and they can't upset the behavior. So the fixed point of the nonlinear system will be asymptotically stable if the eigenvalues of a have negative real part. But if just one of them has a positive real part, then that solution for u would grow exponentially, and you would be unstable. So the tricky case is what happens when you have an eigenvalue with 0 real part, so either equal to 0 or pure imaginary, sitting on the imaginary axis. Unfortunately, this theorem doesn't tell you anything. It just says the fixed point could be stable or unstable. In other words, all bets are off. It's basically much more difficult to tell in that case. So let's explore this through an example. It's the same example we did last time. We found the fixed points. There was 0, 0, 0, 3, and 2, 0. I'm going to have to take the partial derivatives of the right-hand side, so I'll expand those out. 8x minus 4x squared minus xy. This one is 3y minus 3xy minus y squared. So first I form the Jacobian derivative matrix, df dx, df dy. These are partial derivatives, dg dx, dg dy. df dx is 8 minus 8x minus y. df dy is minus x. dg dx is minus 3y. dg dy is 3 minus 3x minus 2y. Now I have to substitute in the values of the fixed points. At 0, 0, the Jacobian derivative is 8, 0, 0, 3. Now that is a diagonal matrix, so it's very easy to find its eigenvalues and eigenvectors. One eigenvalue is 8 with eigenvector eigenvector 1, 0, and the other eigenvalue is 3 with eigenvector 0, 1. So I know immediately what the phase portrait of the linearized system is, and because the eigenvalues do not have 0 real part, that means the phase portrait of the nonlinear system will be very similar. What does it look like? I'm not looking at 3, I'm looking at 0. Everything will be moving away. Very fast. I could draw the rest of it in, but I'm not interested in when x and y are negative. Okay, I need to move on now and do the other other fixed points. There's the Jacobian derivative matrix again. Now I'm going to consider the fixed point 0, 3. And I'm going to get a equal to, plug in x equals 0, y equals 3. I will get 5, 0, negative 9, negative 3. Now this is a lower triangular matrix, so its eigenvalues appear on the diagonal. One eigenvalue is 5. And I do have to do a little bit of work to get the eigenvector. It's 8, negative 9. The other eigenvalue is negative 3. And its eigenvector is 0, 1. So that means the phase portrait near 0, 3 will look like, one eigenvector is in the direction 0, 1. Well, that's the part I already knew about. The other one goes in the direction 8 and negative 9. And I move away. Orbits look like that. And finally, at 2, 0, the Jacobian derivative matrix is negative 8, negative 2, 0, negative 3. Eigenvalues are negative 8 with eigenvector 1, 0, and negative 3 with eigenvector 2, negative 5. So the phase portrait near 2, 0 here everything's going to be falling in. I already know I can fall in that way. The other direction is 2, negative 5. Everything will fall in like that. So there's the phase portrait near that third fixed point, 2, 0. So the conclusion from that theorem 10.3 is that this fixed point at 2, 0 is stable, in fact asymptotically stable, because both eigenvalues have negative real parts. This one at 0, 3 is unstable because there is at least one eigenvalue with positive real part. It's this one here. And the fixed point at 0, 0 is unstable because both eigenvalues have positive real part. So you can see from the drawings I'm actually getting a little bit more than just stable or unstable. I'm actually getting a picture of what the phase portrait looks like near the fixed point. Okay, let's try it again. Okay, second example. Let's see how far the methods that we've done so far can take us to understand this nonlinear planar system. First, I'm going to find the fixed points. From the first equation, x equals 0 or y equals 1. Well, if x equals 0, substitute that into the second equation, you must have y equals 0. Or, from the first equation, you might have y equals 1. Substitute that into the second equation, you must then have x equals 2. So there are two fixed points, 0, 0, and 2, 1. Now I want to get the Jacobian derivative matrix, so I'll expand out those right-hand sides. That's x minus xy. Y dot is 2xy minus 4y. So the Jacobian derivative is df dx is 1 minus y, df dy is minus x, dg dx is 2y, dg dy is 2x minus 4. At 0, 0, substitute in x equals 0, y equals 0, I get 1, 0, 0, negative 4, which means the eigenvalues, it's a diagonal matrix, the eigenvalues are 1 with eigenvector 1, 0, and eigenvalue negative 4 with eigenvector negative 0, 1. So I can use that to draw the phase portrait near 0, 0. It must be moving away in this direction with eigenvalue 1, and down in this direction, and in between it must look like that. It's a saddle. Now that's the phase portrait of the linearized system. It's an unstable saddle, but the theorem tells us that for the nonlinear system, the origin must also be an unstable fixed point. Now we'll try the next one. The next fixed point to consider was xy equals 2, 1, and the Jacobian derivative at that point is 0, negative 2, 2, 0. Go away and find the eigenvalues, and you find plus or minus 2i. They're pure imaginary. So that means that theorem 10.3 does not apply. The linearized system, I know what the phase portrait looks like for the linearized system. It's a center. And the fixed point would be stable. But because the theorem doesn't apply, I cannot conclude anything about the phase portrait near the fixed point for the nonlinear system. So what could I do instead? Well, I could try and have a look at the nullclines. Well, remember that x dot was x 1 minus y, and y dot was y 2x minus 4. Well, that means the nullclines, when x1 minus y is 0, you get x equals 0, y equals 1. That's where x dot is 0. And where y dot is 0, you get y equals 0, x equals 2. So we get nice simple equations for the nullclines. I'll just draw the first quadrant. And I have one at x equals 2. And one at y equals 1. On x equals 2, I must be going horizontally. And from checking the sign, you can get that I'm moving to the left here and to the right here. On x equals 1, I must be moving vertically, and it turns out by checking the sign, I'm moving down here and up here. So again, I get only limited information. I see that in general I'm moving around and around. Here's the other fixed point here at 2, 1. But I don't know if I'm moving around and, for example, spiraling in. That would be a consistent picture, or spiraling out, or neither. So for this fixed point here, the two techniques we've done so far, the nullclines and linearizing, have not told me what the nature of the fixed point is, what the phase portrait looks like nearby. I need something else. And luckily for this particular system, there is something else, although it doesn't work for all systems, but it does work for this particular one. And that is the following. You can actually solve it and find the orbits. You can get dy dx. That will be dy dt divided by dx dt. This is an application of the chain rule. This will be y 2x minus 4 divided by x 1 minus y. And because this ordinary differential equation is now a separable first order equation, I can actually integrate it. I'm going to get 1 minus y over y dy is equal to 2x minus 4 over x dx. I can integrate both sides, and I can get log y minus y on the left is equal to 2x minus 4 log x plus c on the right, and level sets of that implicit solution will tell me the curves that the solutions lie on. Now that's a rather complicated thing to graph by hand, so I've done it on MATLAB with the contour function, and here's what it looks like. So these are the level sets of log y minus 2x plus 4 log x equal to c. Here's the fixed point at 2, 1. I see it is in fact a center. And from checking the signs, I'm moving to the left here, and I'm moving to the right here, just as I got from the null lines. Over here I'm moving down, over here I'm moving up.